Capacitance of two spherical shells. Two conducting spherical shells with a common center C have radii A and B, where A is less than B. The outer shell is grounded. That's the symbol we have right over here. The inner shell is charged positively and has an electric potential V. A. What is the net charge stored on the inner shell? Using Gauss's law, determine the magnitude of the electric field in the region between the shells. That's in there. Determine the potential difference between the spherical shells. Then develop an expression for the capacitance of the system in terms of A, B, Q, and fundamental constants. What is the net charge Q stored on the inner shell? The equation for potential is this: V is equal to KQ over R, and for a shell or for a sphere, you calculate the R from the center of the shell or the sphere as if it were a point charge. So the potential, where R equals A, which is the surface of the sphere, and that's where it is equal to V, is going to be Q over 4 pi epsilon 0 A, where A is the radius of this shell. And notice we've replaced K with 1 over 4 pi epsilon 0. Then we just say the charge is 4 pi epsilon 0 A times voltage. Using Gauss's law, determine the magnitude of the electric field in the region between the shells. Express your answer in terms of the net charge Q. Here's Gauss's law. The enclosed charge is a capital Q. That's the charge on this inner spherical shell. And then we know that the electric field is perpendicular to the area vector at all points on that Gaussian surface. So E dot dA becomes EdA. E is a constant everywhere on that shell. We bring that outside the integral. Then we integrate over the surface area, and we get the surface area of a sphere, which is 4 pi r squared. And here is our electric field between the two shells. Determine the potential difference between the spherical shells. We will use the formula. The potential difference is a negative integral from E dot ds from B to A. We're going to go from B to A only because we've done this problem a few times, and we would like to get a positive potential difference. So when we use the formula for capacitance, which is Q over delta V, we'll get a positive number. So we have VB minus VA, and we put in our value for the electric field, and we know that R dot ds will just be dr, so we'll be integrating in a radial direction of KQ over R squared dr. And that's what we have right here. We take out the constants, and then when you integrate 1 over r squared, you get a negative 1 over r, so the signs cancel, and we're evaluating this integral between A and B, 1 over r, and a little algebra here, and we get the potential difference between the two shells as KQ, parentheses B minus A over AB. Had we integrated the other way, we would have had A minus B, which would have given us a negative potential difference. But again, that's not a big deal. We're just interested in the magnitude here for calculating capacitance. Capacitance then is Q over delta V. We substitute in our value for delta V, and here's our capacitance. Now you might ask, where's the charge on the outer surface, right? Because a capacitor, you need plus charge on one side and a negative on another. Well, you've got this sphere with positive charges here. The outer sphere is grounded. The outer shell is grounded. So what's going to happen? Electrons will flow up until they match and balance all the positive charges. So we have created a capacitor by use of that ground.